Today we're going to derive the period of a physical pendulum. Now, a physical pendulum is a pendulum that isn't just a point mass on a string. It's a continuous mass, such as this rod, and it's going to be pivoted onto a wall right here. And in this particular problem, we're going to have this length be L/3. This length is 2L/3. It's going to have mass M and obviously a length L. We're also going to be using a uniform rod, so the mass is evenly distributed linearly. So there are going to be two parts to being able to find the period of the pendulum. First, you have to find the rotational inertia, which is its resistance to oscillations rotationally. And we're going to have to find the equation of motion using Newton's second law in rotational form, which is torque equals I alpha. So let's start off with the rotational inertia. Rotational inertia is, we're not going to go over why it is in this video, but you have to know that it's the integral of r squared dm. And since this is a uniform rod, the derivative of mass with respect to position on the rod is always going to be the same. So it's going to be a constant number, which we're going to call lambda, which is going to be the linear mass density. So that means that dm is equal to lambda dr. So really, this integral, now we have the variable, the integrand, in terms of what we're taking the integral with respect to, so we can actually integrate it. I'm going to pull the constant out of the integral. Alright, so that's the integral. And of course, since it's rotating about this pivot here, we want the rotational inertia to be about that pivot. So using the parallel axis theorem, we're going to just find the rotational inertia of this segment and add the rotational inertia of this segment. So it's going to be, let's start off with this segment. It's going to be the integral from 0 to L/3 of r squared dr. And we're going to add on the integral from 0 to 2L/3. Okay. And of course, the integral of r squared dr is going to be 1/3 r cubed. So let's just pull this out. So it's going to be 1/3. In fact, I'm going to actually factor out 1/3 here as well. So I'm just going to put in L/3 cubed plus 2L/3 cubed. So that's going to give us 9L cubed over 27, and then times the lambda over 3. Let me make some room here. And we're going to multiply this through. It's going to be L lambda L cubed over 9. Okay. We're going to use the fact that lambda L is equal to the mass. The linear mass density, the density, linearly, you multiply it by the length, you're just going to get what the mass is, because we find lambda is equal to mass over L. Okay. So when we factor this out, it's going to be okay. And this is the mass. I'm sorry, this should be squared. So the rotational inertia is ml squared over 9. Alright, so now we've found the rotational inertia. The next part to be able to find the period of the pendulum is to use Newton's second law. F equals ma. The analogous equation in rotational form is torque equals I alpha. So inertia is the resistance to motion. The resistance to motion times the acceleration is force, and then in rotational terms, torque is going to be the resistance to rotation times the angular acceleration. So there's the analogy between rotational and linear mechanics. So torque is also equal to the force perpendicular to the rod times the distance from that force to the axis of rotation. More formally, it's going to be the cross product of the force and the distance. These are vectors. So the resulting form is going to be another vector, and we're just concerned with the magnitude of that vector. So this is good enough. Okay. So we're gonna be using the perpendicular component times the distance to get what torque is. So we can draw this a little bigger. Here we have the pivot. Now the force, the torque is just going to be coming from the weight, and because this is a uniform rod, we can just use that all the weight is at the center of mass, which is of course at L/2, right here. So we have the weight coming down like this. So let's say the rod has made an angle theta with the vertical. This is the right angle. The torque, as we said, is going to be the perpendicular component of the force times the distance from the axis of rotation, so this is d. So how we're going to find what the force is perpendicular to the rod? We're going to use some geometry. We're going to get that this is also theta. This right here will then be 90 minus theta. So the force perpendicular is going to be mg, it's going to be cosine of 90 minus theta. And of course, the cosine of 90 minus theta is just sine theta. So that's the force that's perpendicular to the rod, times this distance here. So this part right here is L/3. So this distance is going to be, let's see, 3L/6 minus 2L/6 is going to equal L/6. So it means that torque is equal to mgL sine theta over 6. And it makes sense that torque is going to be dependent on theta, because you're going to have a different amount of force perpendicular to the rod for every angle that it's at with the vertical. Of course, if the rod is over here, the torque is just going to be the entire weight, and right as it gets to the bottom here, there's not going to be any torque, because there's not going to be any force perpendicular to the rod at that point. So torque equals I alpha. We already know that torque, using the other definition, is mg L sine theta over 6. So we know the rotational inertia from before. So ml squared over 9 times alpha is equal to mg L sine theta over 6. Okay. So we're going to solve for the equation of motion. Generally, when you're solving for the equation of motion, you're going to get a differential equation where, we'll look into that in a second. So we're going to solve for alpha. Alpha is equal to, well, that mass cancels out, this length cancels out, and we're going to be left with 3/2 g sine theta over L. Okay. Now, the angular acceleration is the second derivative of theta. So we're gonna, since it's the time derivative, it's theta double dot. So this notation indicates that we've differentiated theta with respect to time twice by putting the two dots in there. That's equal to 3g over 2L sine of theta. So this is now our differential equation of motion. And we're going to be using this equation to find the period. So I'm going to make a quick change here. To find the period of the pendulum, I'm going to just substitute omega t here. And you'll see why in a minute. So I use the theta equals omega t, where omega is the angular frequency, and 2 pi over the angular frequency is equal to the period. So this is what we're solving for. So we're gonna solve for the angular frequency first. Now, I'm gonna just show you what the solution to this differential equation is, and I'll show you why it's true. It's not super obvious the first time you see it, but you'll get used to it as you go along. So what this is actually going to be is theta of time is equal to negative sine of the square root of 3g over 2L times time. And the reason why is when you differentiate this twice, because of the chain rule, you're going to be multiplying the derivative of this inside twice. So you're going to be multiplying the square root of 3g over 2L twice to get 3g over 2L here. And of course, the derivative of negative sine is negative cosine. You differentiate that, you're going to get sine again. So that's where the sine comes from. So that's equal to well, see, when you differentiate this twice, you're going to get, as we said, 3g over 2L sine of omega t. And when you differentiate this twice, this is still the same thing here. It's still going to be the square root of 3g over 2L. So this must mean that the angular frequency is equal to the square root of 3g over 2L. And we're basically done. So 2 pi over the angular frequency is just going to be 2 pi square root of 2L over 3g. And that is the period